Hi, welcome back to Math 533, Topics in Euclidean Geometry. In this video, we're going to see how the parallel postulate forces your hand on angle sums in Euclidean geometry. So we'll see this both theoretically, and then we will do a little sort of hands-on experimental proof that is actually very similar in flavor from a mathematical point of view. Okay. So let's start with the statement about the angle sum in Euclidean geometry. So we're given a triangle ABC. And of course, in the triangle, we have three angles. I'm going to call them maybe the purple angle with one tick mark, and the purple angle with two tick marks. And so we have these three angles. Then the statement, as you've most often seen it, is the sum of the angle measures of the interior angles is 180 degrees. So the sum of the interior angles of my triangle is 180 degrees. We haven't really developed a theory of angle measures, at least not yet. So instead what we're going to say is that we can find angles like this, where I have rays and this is congruent to the angle in A, that one's congruent to the angle in B, and this is congruent to the angle in C. And so this alternate statement is there exist, I need to name some of these things. Let's call it O, and I'm going to call that X, Y, Z, and W. So there exist X, O, W, and rays, let's say Y and Z on the same side of the line. So that the angle XOY is congruent to the angle in A, the angle YOZ is congruent to the angle in B, and the angle ZOW is congruent to the angle in C. Right, this is a tedious way of saying the same thing. Basically, we're saying they form a linear triple. Right, so the angles in A, B, and C are congruent to a linear triple. And actually, the proof is going to be exactly that. And so the proof, we proceed as follows. What we do is we draw the straight line. Let me call this line L. Right, so I draw the straight line, the line parallel to the base here, AC, incident to B. That exists by the parallel postulate. And I'm going to throw some points on here. Let me call that point here C prime, and let's call this one A prime. Right, so doing that, we get, and so let's let A prime be on L, and I want it to be opposite. Right, it's on the other side of the line BC from A. And similarly, we let C prime be on the line L, and I want it to be opposite the line AB from C. And so that my picture on the left here matches the words that I've written. And then what we do is we say, okay, then by the converse to the alternate interior angles theorem, we have that angle C prime BA is congruent to the angle BAC. Right, that's a pair of alternate interior angles right there. Good. Same deal over here. We have a pair of alternate interior angles. And so the same argument. Okay, so now we have those guys there, but then by construction, we have a linear triple. And we're done, right? So that's a surprisingly quick and beautiful proof of the fact that the sum of the angles in the triangle being 180 degrees follows from this parallel postulate. And we used the parallel postulate twice in here, right? We used it in this first step to say what this line L was, and then we used it quite aggressively here because we invoked the converse to the alternate interior angles theorem, which, as we said before, requires the parallel postulate, right? So we've used the parallel postulate quite extensively in this proof. Something we won't do in this class, but that is true, is that if you know that every triangle has the interior sums of 180 degrees, and you're in neutral geometry, then you can prove that the parallel postulate follows from that. So in some deep sense, this is equivalent to the parallel postulate. I mean, one needs to say that carefully, but it contains the same amount of information as the parallel postulate. Okay, let's take a look at a construction here where we do an experimental approach to the triangle sum. This is an activity you may have done with students in the past, or you may well find it useful to do with students in the future. So let's take a look at it. This is my Euclidean triangle experiment here. So I took a paper plate and I cut out a triangle from it, and then I drew around the edges to mark it on my paper here. So now what I'm going to do is I'm going to take this and I'm going to tear it. I'm going to tear two of the vertices off. So let's say these two vertices, and I'm going to stick my triangle back on the paper where it was, and we're going to stick the angles now next to it. So I'm going to stick this one here, and this one here. Okay, it's a little bit fussy. Maybe let me grab a ruler. Okay, the three of them line up if I'm a little bit more careful with that than I was. And if we look carefully, right, we see how they line up nicely like that. If I had done it like so, very nicely we see the line that I constructed in the proof of the theorem. This line here, and I'm going to take my Sharpie and try to trace over it. In the process, I disrupted it. There we go. That's pretty close, right? I arguably should make that line up correctly. So now my red line is the line I get from those three angles that I started with. I'll go put them back to where they were. And if you notice, my red line is parallel to that line right there, which is exactly what we had in our proof of the theorem, except in some sense we're doing the opposite here. So this is an empirical verification of it rather than a proof. And the equipment used is very inexpensive, as you can see. So it's a great thing to use perhaps in a class with some students. Okay, let's jump back now to some theory. So we're going to define a quadrilateral. This is a little bit painful, but our goal now is to talk a little bit about parallelograms. Okay, so a quadrilateral consists of four distinct points that are going to be the vertices. We think of them as coming with a cyclic ordering. So a cyclic ordering means that B follows A, let's say, C follows B, D follows C, and then A follows D, etc. Right, so I just want to be able to do that so we can talk about the next or previous vertex. We actually don't care about which direction we go, we just care about who is next to who. Then our quadrilateral has four sides. We have the four segments, AB, BC, CD, and DA. And we have a bunch of conditions. So our first condition is we're not allowed to have consecutive vertices in our cyclic ordering be collinear. So I've listed the four triples of vertices that are not allowed to be collinear. And furthermore, sides only intersect at a shared endpoint if they share an endpoint. So these are what we call adjacent sides. And then for this, we write this little box, ABCD. And we say that two quadrilaterals are congruent if we have a correspondence of vertices that allows us to send corresponding sides to corresponding sides and corresponding angles to corresponding angles in such a way that all of those correspondences are congruences. So let's draw some pictures of quadrilaterals. Right, so sort of a very normal looking quadrilateral. A less normal looking quadrilateral. So the one on the left is what's called a convex quadrilateral. The one on the right is not convex. We'll maybe talk about that at some other point. Right now, let's not focus on that. So these are examples. So let me give us green check marks for both of those. And now let's draw some that are bad. So this is bad because the sides cross each other not at a shared vertex. So that's bad. The next thing that's bad is we are not allowed to have a triangle with an extra point on it. Right, this one's bad because A, B, and C happen to be collinear in this picture. Right, so the top row are good, the bottom row are both bad because they violate our rules. So now we make a definition. We say that a quadrilateral ABCD is a parallelogram if the opposite sides are parallel 2 by 2. And so if I have some picture that looks like that, right, I'm going to pretend that that's parallel. Right, this is A, B, C, D. We have that AB is parallel to CD, and we have that AD is parallel to CB. Right, that's my definition of a parallelogram. So here we have a whole mess of facts about parallelograms that you'll prove on the homework. And actually, in Euclidean geometry, these things are if and only ifs. So some of these you will prove on the homework. In general, the ones you don't prove, if it's not a question I'm asking you on a homework assignment, you can just go ahead and use it without proof. So we have, for instance, congruence of triangles. If I look at one of the diagonals of my parallelogram, it slices the parallelogram into a pair of congruent triangles. The opposite sides are going to be congruent to each other. The opposite angles are congruent to each other. And then finally, the diagonals intersect in their respective midpoints. So what that means is the two diagonals intersect, and that point of intersection divides each diagonal individually into two congruent halves. Right? It's not saying anything about congruence of the diagonals between each other. Okay, so that's something you will take a look at on the homework. Okay, that's it for this video. I hope you enjoyed. I hope you learned something. Happy mathing, and see you on the next one.